Hi there, welcome back. In this slice of physics, we're going to talk about electric potential. That's a new concept, and we'll introduce that by building on your familiarity with potential energy. You're familiar with gravitational potential energy with masses. So we'll first talk about electric potential energy, which is the energy when you have two charges that are placed near each other. We will look at the work considerations in this environment as we move a charge around another fixed charge. And based on these concepts, we will introduce electric potential and see how it's related to, but importantly different from, electric potential energy. Since we're going to be introducing a few new concepts, let's start in a familiar place. So let's say this is the Earth with a mass of m, and I've got another mass, a ball of mass lowercase m, that is over here. So when it's at this point, let's call this point number 1, it has a potential energy. In fact, the Earth-ball combination has a potential energy. We need at least two masses to have gravitational potential energy. So let's call that UG1. U for potential energy, G for gravitational potential energy, and 1 for the potential energy at point 1. You know that if we let this ball go, it's going to drop down to the Earth. And so let's take another point 2 here that's closer to the surface of the Earth, and the potential energy of the ball-Earth combination at that point can be written as UG2. And you know from Physics 1 that UG1 is greater than UG2. The higher you are, the more your potential energy. So a key observation from here that's very useful as you think about potential and potential energy for charges is that if released from rest, a mass will move to a point where its potential energy is lower. Also, in order for me to move the ball from point 2 to point 1, I have to raise its potential energy, increase its potential energy, which means I have to do work on it. You can think of this as me putting my hand under the ball, and so the normal force from my hand on the ball is acting in the upward direction, and as I move the ball in the upward direction, the displacement and the force are aligned, so that gives me a positive work, and a positive work goes into increasing the potential energy of the Earth ball system. And rather than drop it at point 1, if I were to steadily lower it, the normal force from my hand is still upward, the displacement is downward. So if I go from point 1 to 2 at a steady speed, my work done would be negative. Force and displacement are in opposite directions, which gives me a negative work, and that implies a decrease in potential energy. So that's a quick review of Physics 1 concepts, and it's interesting to see that very similar things happen in charges. So for the charge analogy, I'm going to take a negative charge sitting here at the bottom, and the charge that we're going to play with in terms of moving it is, let's say, a positive charge at point 1 and at point 2. Now, left to its own devices, if we have the positive charge at point 1 and we simply let go, it's going to go towards the negative charge. Positive and negative attract each other, so it's going to fly down, similar to what the ball did over there. And so this is the first observation that is analogous to the gravitational sense. If a charge is released from rest, it will also go to a lower potential energy, but in this case we're talking about electric potential energy. So at this point 1 I've got UE1, and at point 2 I've got UE2. Electric potential energy at point 1 and electric potential energy at point 2. And the potential energy of these two charges is higher at point 1 than at point 2. So I've got UE1 is greater than UE2. And continuing this analogy, if I move the positive charge from point 2 to point 1, it doesn't want to go there by itself. It wants to go closer to the negative charge, but I can grab it and apply a force and move it. So I can put my hand below it and raise my hand and move the charge up. And as I do that, as I move this charge from 2 to 1, the work I do on it is positive because the force from my hand is upward, the displacement is upward. That gives me a positive work, which results in an increase in potential energy as it goes from 2 to 1. And to finish up this thing, if I move from 1 back to 2 at a steady speed, so I lower it steadily from 1 to 2, I got to place my hand over here. And so the force from my hand is upward, the displacement is downward, so the work is negative in that case, which implies a decrease in potential energy. And just to clarify, I'm going to put a UE over here to say that we are now talking about electric potential energy and not gravitational potential energy. Okay, so that's convenient in terms of seeing all that analogy, but working with charges turns out to be more complex than working with masses, because all masses are the same kind and all masses attract all other masses. But you know that we have two types of charges, and unlike charges attract and like charges repel. So if I had a situation here where rather than this fixed charge being a negative charge, if it was a positive charge, and my probe charge is still positive, so now if I've got these points 1 and 2, at which point do I have a higher electric potential energy? So I've got UE1 over here and UE2 over here. We can't automatically assume that higher the point is, higher the potential energy. That's no longer true when we're dealing with charges. The geography of what's higher or lower is immaterial. That only made sense when we were talking about masses near the surface of the Earth. But this fact here that we wrote down seemed trivial when we wrote it, but you'll see how useful it is now. That part is still true. So if I release a charge from rest, it's going to go to a place where it has lower potential energy. If I have the charge at point 2 and I release it, you know that it's going to be repelled by the fixed charge, so it's going to go from 2 to 1. So a free charge, when released from rest, will go from 2 to 1. It won't go from 1 to 2. And so that tells us that potential energy at point 1 has to be lower than the potential energy at point 2, because this fact is always true. When you release a charge from rest, it goes to a lower potential energy. So going from 2 to 1 tells us that UE1 is in this case less than UE2. Opposite conclusion from what we had before. So now if I want to move the free charge from 2 to 1, that's where it wants to go anyway. It'll fly if I let it loose. But if I want to steadily move it, first I got to place my hand over here to block this charge from flying away, and then I got to slowly ease my hand upward to move it in a steady manner. The force from my hand on the charge is going to be acting down, the displacement is up, and because they are opposite, the work in this case would be negative, which means the potential energy decreases. And then if I have the charge at point 1 and I want to bring it to point 2, it doesn't want to go that way. It doesn't want to get closer to another positive charge. So in order to do that, I'm going to have to place my hand above the charge and push it down. So the normal force from my hand on the charge is down, displacement will be down, so that'll give me a positive work, and as a result, an increase in potential energy. So our next step is to introduce electric potential, and in order to do that, I'm going to take some numbers for these potential energies. I'm going to make up some numbers that are directionally correct and introduce electric potential from that concept. So let's say I've got a fixed positive charge over here. This is fixed, it's not going anywhere. And then I've got a loose positive charge over here that's free to move. So if I've got a location for this charge here and another location for this charge here, and let's number these points as 1 and 2, you now know that UE2 is less than UE1. That's based on this fact that if I release a charge from rest, it's going to fly to a position of lower potential energy. Let's give it some values. You know that potential energy is a type of energy, and so the SI units for it are joules. And so let me say that the potential energy at this point 1 is 200 joules, and at point 2 is 150 joules. Now you saw that in order to have potential energy, I need to have at least 2 charges. If I just had one single charge in the entire universe, there is no concept of potential energy. Just like if I only had one mass, there would be no potential energy. You need at least 2 masses to have potential energy. So let's note that fact down over here. Need at least 2 charges to have electric potential energy. But if we now ask, what happens if we just had 1 charge? Do we still have anything, and what might that be? Well, going back to the gravitational example, if we just had 1 mass, and if we had hills and valleys, that 1 mass can create a terrain. And in that terrain, if you place another mass, you can have different potential energies at different points. You don't need another mass to have this terrain, but you do need another mass to have potential energy. Well, this terrain in the gravitational sense is what's called gravitational potential, and you only need 1 mass for that. And there's an equivalent of that in the electric sense, which is called electric potential. And so you only need 1 charge to create electric potential around it. So the definition of electric potential, and by the way, the symbol for electric potential is capital letter V, and it's defined as the electric potential energy at one point that a charge would have divided by the charge itself. So if this charge here was charge Q, the electric potential V is defined as electric potential energy divided by the charge Q. So naturally, the units of electric potential will be whatever the units of potential energy are, which are joules divided by coulomb. That's the unit of electric potential, and we give that a name. That's called volt, and it also has a symbol of capital V. So electric potential is measured in volts, and so when you talk about a battery with a 1.5 volt, you're talking about the electric potential between the positive and the negative ends of the battery. So let's say in this example, if my Q was 10 coulomb, so then the potential at point 1 would simply be 200 divided by 10. So the V1 here would be 20 volts, and V2 would be 150 joules divided by the same 10 coulombs, so 15 volts. And that terrain of 20 volts and 15 volts was created by this other fixed charge. Just like this mass of the Earth and the terrain created gravitational potential differences at various points. Okay, one last concept I want to cover before we wrap up this video. In the gravitational sense, when you have a terrain, the top of a hill has a higher potential than the bottom of the hill, and that's always fixed. The higher you are, the more potential you have. The lower you are, the less potential you have. In the electric sense, because we have 2 types of charges, it's not that straightforward a relationship. What happens is that when you have a positive charge, it creates an electric potential near it, such that as you move farther away from the charge, the potential drops. And it drops in a curved fashion, as we will see later, like that. And if you have a negative charge, so in that sense, you can say that a positive charge sits at the top of an electric potential hill. A negative charge, on the other hand, sits at the bottom of an electric potential valley. And the terrain looks like that. The farther you go from the negative charge, the higher the electric potential. So let me identify some things here. In a positive charge, as you go farther away from it, you are going towards a lower electric potential. And in a negative charge, as you go away from it, you are going to a higher electric potential. Lastly, let's see what happens to potential energy in these various cases. Well, if I have a loose positive charge, you leave here, it's going to go to an area where it has lower potential energy, so it's going to go farther away from the other positive charge, so it's going to go this way and have a decreasing potential energy as it does that. But you can see that if I leave a negative charge loose over here, it's going to climb up the potential hill, but if I leave it loose and it moves towards a positive charge, it's going to still lower its potential energy. So by going up a potential hill, the potential energy of the negative charge will go down. This can all be a bit confusing, and it's going to take some practice to get your arms around this. But the reason I started with this important fact here is that is your anchor. That's always going to get you to the right answer. If you let anything loose and release it from rest, it's going to automatically go to a position where its potential energy will be lower. That part is always true. And finally, let's just finish up the discussions here with a positive charge. If I let a positive charge loose over here, it's going to go in this direction, and as it does that, its potential energy is going to be lower as it goes down the potential valley. And if I leave a negative charge loose over here, it's going to want to fly to a higher electric potential point, but as it does that, its potential energy is still decreasing because it's going where it wants to go spontaneously. Okay, that was a lot, so let me quickly summarize the key points about electric potential. First, we saw that we need at least two charges to have electric potential energy, but one charge is enough to create an electric potential terrain around it. And then we used the mass analogy, but saw that working with charges can be a little more complex because there are two kinds of charges. So you got attractive and repulsive forces. But the one fact that was always true is that when released from rest, all charges, positive and negative, move to a point where they will have a lower potential energy. Now, where it gets tricky is that for positive charges, that also means that they move to a lower electric potential. So positive charges roll down a potential hill, whereas negative charges have to climb up to a higher electric potential point in order to decrease their potential energy. So negative charges will roll up a potential hill when let loose, like helium balloons do near the surface of the Earth. So that's what happened to the free charge. Now, what created the potential terrain was a fixed charge, and we saw that positive charges sit at the top of a potential hill. So as you move away from a positive charge, the potential decreases, whereas negative charges sit at the bottom of a potential valley. So as you move away from a negative charge, the potential in fact increases. Finally, we defined electric potential as this italicized V, and we said it's measured in SI units of volts. We saw that the electric potential is potential energy divided by charge, and the unit of 1 volt is simply the same as 1 joule over Coulomb. Thanks.